Semi-supervised learning refers to methods that train models using a combination of labeled and unlabeled data. It sits between supervised and unsupervised learning. This video explains why this approach exists and how it helps address practical data constraints in real-world AI systems. This approach blends guidance and discovery. A small set of labeled examples provides direction, while a larger pool of unlabeled data supplies additional structure and context. Semi-supervised learning exists because labeled data is expensive and time-consuming to produce, while unlabeled data is abundant. Many real-world datasets reflect this imbalance. Typically, only a fraction of available data is labeled. The goal is to leverage unlabeled examples to improve learning without incurring full labeling costs. A key assumption is that similar inputs should have similar outputs. This assumption allows models to infer labels based on data structure. The objective is to improve predictive accuracy while reducing reliance on labeled data. Efficiency is central to this approach. Labeling requires human effort and domain expertise. This makes large-scale annotation impractical in many domains. Semi-supervised learning is common in domains like vision and language, where raw data is plentiful but annotation is costly. A typical workflow begins with training on labeled data, then gradually incorporating unlabeled examples into learning. Unlabeled data helps models learn structure and representation, even without explicit targets. The consistency assumption states that predictions should remain stable under small input changes. The cluster assumption suggests that data points in the same cluster share labels. Low-density separation assumes decision boundaries lie in regions with few data points. Pseudo-labeling assigns model-generated labels to unlabeled data. These labels are used cautiously in further training. Confidence thresholds limit which pseudo-labels are accepted, reducing error propagation. Self-training allows models to iteratively refine predictions by learning from their own outputs. Graph-based methods propagate labels across similarity networks constructed from data. Neural networks often use pre-training followed by supervised fine-tuning, a semi-supervised pattern. Pre-training learns general representations that reduce dependence on labeled data. Transfer learning reuses knowledge from related tasks, further reducing labeling requirements. In vision, a few labeled images combined with many unlabeled ones can significantly improve accuracy. In language tasks, limited annotations can be amplified using large text corpora. Compared to fully supervised learning, this approach lowers cost and improves generalization. Incorrect pseudo-labels can amplify errors. Careful validation is necessary. Quality control includes validation sets and selective human review. Results depend heavily on assumptions about data structure and distribution. Data drift can break these assumptions, reducing effectiveness over time. Training can be computationally expensive due to iterative processes. Evaluation remains challenging because labeled benchmarks are limited. Ethical risks include bias amplification when incorrect labels spread. Semi-supervised learning works best when data exhibits clear structure. It performs poorly when structure is weak or noise dominates. Compared to supervised learning, fewer labels are needed, but more assumptions are required. Compared to unsupervised learning, labels provide guidance and direction. Industry adoption reflects cost constraints and data realities. Human oversight remains important to correct drift and errors. Modern frameworks increasingly support semi-supervised techniques. Large-scale models rely heavily on pre-training, a semi-supervised strategy. Semi-supervised learning plays a central role in modern foundation models. A misconception is that it offers free performance gains without risk. Interpretability becomes more difficult due to indirect supervision. Governance mechanisms must address reduced transparency. Monitoring helps contain errors and prevent runaway feedback loops. Maintenance includes retraining and reassessment as data evolves. Strengths include efficiency, scalability, and practicality. Limitations include assumption sensitivity and error amplification risk. The key idea is that labels guide learning while data fills gaps. This approach balances practicality and performance in real-world settings. Semi-supervised learning bridges the gap between other learning paradigms. Next, we examine reinforcement learning, where agents learn through interaction and reward.